The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
I want to pick up exactly where I left off last time when I was talking about various sins one can commit with statistics. And I had been talking about the sin of data enhancement. Where the basic idea there is you take a piece of data and you read much more into it than it implies. In particular, a very common thing people do with data is they extrapolate. And I've given you a couple of examples. In the real world, it's often not desirable to say that I have a point here and a point here, therefore the next point will surely be here. And we can just extrapolate in a straight line. We before saw some examples where I had an algorithm to generate points and we fit a curve to it, used the curve to predict future points and discovered it was nowhere close. Unfortunately, we often see people do this sort of thing. One of my favorite stories is William Ruckelshaus, who was head of the Environmental Protection Agency in the early 1970s. And he had a press conference, spoke about the increased use of cars and the decreased amount of carpooling. He was trying to convince people to carpool, and at the time, carpooling was on the way down. And I now quote, each car entering a central city, in 1960, he said, each car entering a central city had 1.7 people in it. By 1970, this had dropped to less than 1.2. If present trends continue, by 1980, more than 1 out of every 10 cars entering a city will have no driver. Amazingly enough, the press reported this as a straight story and talked about how we would be dramatically dropping. Of course, as it happened, it didn't occur. But it's just an example of how much trouble you can get into by extrapolating. The final sin I want to talk about is probably the most common. And it's called the Texas sharpshooter fallacy. Now, before I get into that, are any of you here from Texas? All right, you're going to be offended. Let me think. Is anybody here from Oklahoma? You'll like it. I'll dump on Oklahoma. It'll be much better then. We'll talk about the Oklahoma sharpshooter fallacy. We won't talk about the BCS rankings, though. So the idea here is a pretty simple one. This is a famous marksman who fires his gun randomly at the side of a barn, has a bunch of holes in it, then goes and takes a piece of can of paint and draws bullseyes around all the places his bullets happen to hit. And people walk by the barn and say, God, he is good. So obviously not a good thing, but amazingly easy to fall into this trap. So here's another example. In August of 2001, a paper, which people took seriously, appeared in a moderately serious journal called The New Scientist. And it announced that researchers in Scotland had proven that anorexics are likely to have been born in June. I'm sure you all knew that. How did they prove this or demonstrate this? They studied 446 women. each of whom had been diagnosed as anorexic. And they observed that about 30% more than average were born in June. Now, since the monthly average of births, if you divide this by 12, is about 37, that tells us that 48 were born in June. So at first sight, this seems significant. And in fact, if you run tests and ask what's the likelihood of that many more being born in 1 month, you'll find that it's quite unlikely. In fact, you'll find the probability of this happening is only about 3% of it happening just by accident. What's wrong with the logic here? Yes?
They only study of diagnosed anorexics?
No, because they were only interested in the question of when are anorexics born. So it made sense to only study those. Now, maybe you're right that we could study that, in fact, more people are born in June, period. So that would be true. This would be one of the fallacies we looked at before, right? That there's a lurking variable, which is just that people are more likely to be born in June. So that's certainly a possibility. What else? What else is the flaw? Where's the flaw in this logic? Well, what did they do? They participated in the Oklahoma sharpshooter fallacy. What they did is they looked at 12 months. They took the months with the most births in it, which happened to be June, and calculated the probability of 3%. They didn't start with the hypothesis that it was June. They started with 12 months, and then they drew a bullseye around June. So the right question to ask is, what's the probability, not that June had 48 babies, but that at least one of the 12 months had 48 babies? That probability is a lot higher than 3%, right? In fact, it's about 30%. So what we see is, again, perfectly reasonable statistical techniques, but not looking at things in the right way and answering the wrong question. Does that make sense to everybody? And you can see why people can fall into this trap, right? It was a perfectly sensible, seemingly sensible argument. So the moral of this particular thing is be very careful about looking at your data, drawing a conclusion, and then saying, how probable was that to have occurred? Because, again, you're probably, or maybe, drawing the bullseye around something that's already there. Now, if they had taken another set of 446 anorexics, and again June was the month, then there would be some credibility in it. Because they would have started with the hypothesis, not that there existed a month, but that June was particularly likely. But then they would have had to also check that and make sure that June isn't just a popular month to be born, as was suggested earlier. All right. I could go on and on with this sort of thing. It's kind of fun, but I won't. Instead, I'm going to torture you with yet one more simulation. You may be tempted at this point to just zone out. Try not to. And as an added incentive for you to pay attention, I'm going to warn you that this particular simulation will appear in the final. And in fact, a variant of it. And what we'll be doing is early next week we'll be distributing code, which we'll ask you to study, about 2 or 3 pages of code. And then on the final, we'll be asking you questions about the code. Not that you have to memorize it, we'll give you a copy of it. But you should understand that before you walk in to take the final, because there will not be time to look at that code for the first time during the quiz and figure out what it's doing. Okay? So let's look at it. I should also warn you that this code includes some Python concepts, at least one, that you have not yet seen. We'll see it briefly today. This is on purpose, because one of the things I hope you have learned to do this semester is look up things you don't know and figure out what they do, what they mean. Because we obviously can't, in any course, or even any set of courses, tell you everything you'll ever want to know in life. So intentionally, we've seeded some things in this program that will be unfamiliar. So during the time you're studying the program, get online, look it up, figure out what they do. If you have trouble, we will be having office hours where you can go and get some help. But the TAs will expect you to have at least tried to figure it out yourself. Yeah?
Will the final be open note?
Final will be open book, open notes, just like the quizzes. It will be the first 2 hours of the allotted time. We won't go the whole 3 hours. Okay? So it won't be hugely longer than the quizzes. It'll be a little bit longer. And again, very much in the same style of the quizzes. All right. Let's look at this. Let's assume that you have won the lottery and have serious money that you foolishly wish to invest in the stock market. There are 2 basic strategies to choose from in investing. You can either have what's called an indexed portfolio, or a managed portfolio. Index portfolios, you basically say, I want to own all of the stocks that there are, and if the stock market goes up, I make money. If the stock market goes down, I lose money. I'm not going to be thinking I'm clever and can pick winners and losers. I'm just betting on the market as a whole. They're attractive in that, A, they don't require a lot of thought, and B, they have what's called a low expense ratio. Since they're easy to implement, you don't pay anyone to be brilliant to implement it for you, so they're very low fees. A managed portfolio, you find somebody you think is really smart, and you pay them a fair amount of money, and in return, they assert that they will pick winners for you, and that, in fact, you will outperform the stock market. And if it goes up 6%, well, you'll go up 10% or more. And if it goes down, don't worry, I'm so smart, your stocks won't go down. There's a lot of debate about which is the better of these 2. And so now we're going to try and see if we can write a simulation that will give us some insight as to which of these might be better or worse. All right? So that's the basic problem. Now, as we know, and by the way, we're not going to write a perfect simulation here, because we're going to try and do it in 40 minutes or 30 minutes. And it would take at least an hour to do a perfect simulation of the stock market. All right. First thing we need to do is have some sort of a theory. Now, when we did the spring, we had this theory of Hooke's law that told us something, and we built a simulation or built some tools around that theory. Now we need to think about a model of the stock market. And the model we're going to use is based on what's called the efficient market hypothesis. So the moral here, again, is whenever you're doing a implementation of a simulation, you do need to have some underlying theory about the model. What this model asserts is that the markets are informationally efficient. That is to say, current prices reflect all publicly known information about each stock and therefore are unbiased. That if people thought that the stock was underpriced, well, people would buy more of it and the price would have risen already. If people thought the stock was overpriced, well, people would have tried to sell it and it would have come down. So this is a very popular theory believed by many famous economists today and in the past, and says, okay, that effectively means that the market is memoryless. Okay, that it doesn't matter what the price of the stock was yesterday. Today it's priced given the best known information, and so tomorrow it's equally likely to go up or down relative to the whole market. Right? It's well known that over periods of multiple decades, the market has a tendency to go up. And so there's an upward bias to the stock market, contrary to what you may have seen recently. But that no particular stock is more or less likely to outperform the market because we already have all the information is incorporated in the price. And that leads to a notion of being able to model the market how? How would you model individual stocks if you believed this hypothesis? Somebody? What's going to happen?
Random walk.
Yes, exactly right. So we would model it as a random walk. And in fact, there's a very famous book called A Random Walk Down Wall Street that was one of the first to make this hypothesis. Now, later we may decide to abandon this model, but for the moment, let's accept that. And let's think about how we're going to build this simulation. Well, whenever I think about how to build an interesting program, and I hope whenever you think about it, the first thing I think about is what are the classes I might want to have? What are the types? And it seems pretty obvious that at least two of the things I'm going to want are stock and market. After all, I'm going to try and build a simulation of the stock market, so I might as well have the notion of a market and probably the notion of a stock. Which should I implement first? Well, my usual style of programming, it would be to implement the one that's lowest down in the hierarchy, near the bottom. I won't be able to show you what a market does unless I have stocks, but I can look at what an individual stock does without having a market. So why would I implement this first? Because it will be easier to unit test. I can build class stock and I can test class stock before I have a class market. So now let's look at it. Clean up the desktop a little bit. This is similar to, but not identical to what you have on your handout. Get rid of that. All right. So there's class stock. And I'm going to initialize it, create them, with an opening price. When a stock is first listed in the market, it comes with some price. I'm going to keep, as part of each stock, its history of prices, which we can initialize. Well, I've initialized it as empty, but that's probably the wrong thing, right? I probably should have had it being the starting here, right? The opening price. Now comes an interesting part. Self-dot distribution. Well, I lied to you a little bit in my description of what it meant to have an efficient market hypothesis. I said that no stock is likely to outperform the market or underperform the market. But it's not quite true, because typically what they actually do that is they say it's adjusted for risk. It's clear that some stocks are more volatile than others. If you buy stock in an electrical utility, which has a guaranteed revenue stream, because no matter how bad the economy gets, a lot of people will still use electricity, you don't expect it to fluctuate a lot. If you buy stock in a high-tech company that sells things on the internet, you might expect it to fluctuate enormously. Or if you buy stock in a retailer, you might expect it to go up or down more dramatically with the economy. And so, in fact, there is a notion of risk, and I'm not going to do this in this simulation, but usually people have to be paid to take risk. And so it's usually the case that you can get a higher return if you're willing to take more risk. We might or might not have time to come back to that. But more generally, the point is that each stock actually behaves a little bit differently. There's a distribution of how it would move. So even if on average the stock is expected to not move at all from where it starts, some stocks will be expected to just trundle along without much change, not very volatile. And other stocks might jump up and down a lot because they're very volatile. Even if the expected value is the same, they'd move around a lot. So how can we model this kind of thing? Well, we've already looked at the basic notion. Last time we looked at the notion, last lecture, we looked at the idea of a distribution. So when we do a simulation, we're pulling the samples from some distribution. It could be normal, everything, that would be a Gaussian, where, if you'll recall, there was a mean and a standard deviation, and most values were going to be close to the mean, especially if there is a small standard deviation. If there is a large standard deviation, it would be spread. Or it could be uniform, where every value was equally probable. We also looked at exponential. So we're going to assign to each stock, when we create it, a distribution, some way of visualizing or thinking about where we draw the price changes from. This gets us into a new linguistic concept, which we'll see down here. You don't have this particular code on your handout. You do have a code that uses the same concept. So here's my unit test procedure. And here's where I'm going to create distributions. And I'm going to look at two: a random, or a uniform, and a Gaussian. What lambda does is it creates on the fly a function as the program runs. and that I can then pass around. So here, I'm going to look at the thing random.uniform, for example, between minus volatility and plus volatility. So ignoring the lambda, what do we expect random.uniform to do? It has equally likely in the range from minus volatility to plus volatility, it will return any value in here. But notice the previous line where I'm computing volatility. If I wanted every stock to have the same volatility, I could just do that, if you will, at the time I wrote my program. But here I want it to be determined, chosen at runtime. So first, I choose a volatility randomly from some distribution of possible volatilities from 0 to, in this case, 0.2. Think of this as the percentage move per day. So 0.2%, as would be the move here. And then I'll create this function, this distribution d1, which will, whenever I call it, give me a random, uniformly selected value between minus and plus volatility. Then when I create the stock here, I can pass it in, pass in d1. Okay, it's a new concept. I don't expect you'll all immediately grab it, but you will need to understand it before the quiz comes along. And then I could also do a Gaussian one here with a mean of 0 and a standard deviation of volatility divided by 2. Where do these parameters come from? I made them up out of whole cloth. Later we'll talk about how one could think about them more intelligently. Now, what do I do with that? All right, we'll see that in a minute. But if people understand what the basic idea here is. Now, I can set the price of a stock. And when I do that, I'll append it to history. I can, these have got some remnants which we really don't need. I'll get rid of this, which is just a uninteresting thing. And let's look at make move. Because this is the interesting thing. Make move is what we call to change the price of a stock at the beginning or end of a day, if you will. So the first thing it does is it says if self.price is 0, I'm just going to return. This is not the right thing to do, by the way. Again, there are some bugs in here. You won't find these bugs in your handout, right? The code is different in the handout. But I wanted to show these to you so we could think about what I'm more interested in here than in the result of the simulation is the process of creating it. So why did I put this here? Why did I say if self.price equals 0, return? Because the first time I wrote the program, I didn't have anything like that here, and a stock could go to 0 and then recover, or even go to negative values. Well, we know stock prices are never negative. And in fact, we know if the price goes to 0, it's delisted from the exchange. So I said, all right, we better make a special case of that. It turns out that this will be a bug, and I want you to think about why it's wrong for me to put this check here. The check needs to be somewhere in the program, but this is not the right place for it. So think about why I didn't leave it here. Okay, then we'll get the old price, which we're going to try and remember. And now comes the interesting part. We're going to try and figure out how the price should change. So I'm first going to compute something called the base move. Think of this as kind of the basis from which we'll be computing the actual move. I'll draw something from the distribution. So this is interesting. I'm now calling self.distribution. And remember, this will be different for each stock. It will return me some random value from either the Gaussian or the normal distribution, with a different volatility for the stocks, because that was also selected randomly, plus some market bias, saying, well, the market on average will go up a little bit or go down a little bit. And then I'll set the new price, if you will, self.price to self.price times 1 plus the base move. So notice what this says. If the base move is 0, then the price doesn't change. So that makes sense. Interesting question. Why do you think I said self.price times 1 plus the base move rather than just adding the base move to the stock price of the stock? Again, the first time I coded this, I had an addition there instead of a multiplication. What would the ramification of an addition there be? That would say how much the stock changed is independent of its current price. And when I ran that, I got weird results. Because we know that a Google priced at, say, 300 is much more likely to move by 10 points in a day than a stock that's priced at 50 cents. So in fact, it is the case if you look at data. And by the way, that's the way I ended up setting a lot of these parameters and playing with it, was comparing what my simulation said to historical stock data. And indeed, it is the case that the price of the stock, the amount of the move tends to be proportional to the price of the stock. Expensive stocks move more. Interestingly enough, the percentage moves are not much different between cheap stocks and expensive stocks. And that's why I ended up using a multiplicative factor rather than an additive factor. This is, again, a general lesson. As you build these kinds of simulations or anything like this, you need to think through whether things should be multiplicative or additive, because you get very different results typically. Multiplicative is what you want to do if the amount of change is proportional to the current size, whether it's price or anything else, and additive if the change is independent of the current value, typically, is I think, the general way to think about it. Now, you'll see this other kind of peculiar thing. So I've now set the price, and then I've got this test here. If MO stands for momentum, I'm now exploring the question of whether or not stock prices are indeed memoryless, or the stock changes. And the fancy word for that is Poisson. People often model things as Poisson processes, which is to say processes in which past behavior has no impact on future behavior. It's memoryless. And in fact, that's what the efficient market hypothesis purports to say. It says that since all the information is in the current price, you don't have to worry about whether it went up or down yesterday to decide what it's going to do today. There are people who don't believe that and instead argue that there is this notion called momentum. These are called momentum investors. And they say what's most likely to happen today is what happened yesterday. or more likely. If the stock went up yesterday, it's more likely to go up today than if it didn't go up yesterday. So I wasn't sure which religion I was willing to believe in, if either. So I added a parameter called, if you believe in momentum, then you should change the price by, and here I just did something taking a Gaussian times the last change, and in fact added it in. So if it went up yesterday, it will more likely go up today because I'm throwing in a positive number, otherwise a negative number. Notice that this is additive because it's dealing with yesterday's price, change, with the change. Okay? So that's why we're dealing with that. Now here's where I should have put in this test that I had up here. Get it out from there. Because what I want to do is say is if self.price is less than 0.01, I'm going to set it to 0. Just keep it there. That doesn't solve the problem we had before, though, right? Then I'm going to append it and keep the last change for future use. Okay, people understand what's going on here? And then show history is just going to produce a plot. We've seen that a million times before. Any questions about this? Well, I have a question. Does it make any sense? Is it going to work at all? So now let's test it. So I now have this unit test program called unit test stock. I originally did not make it a function. I had it in line, and I realized that was really stupid because I wanted to do it a lot of times. So it's got an internal procedure, an internal function, local to the unit test, that runs the simulation. And it takes the set of stocks simulate a figure number. This is going to print a bunch of graphs, and I want to say what graph it is, and whether or not I believe in Big Mo. It sets the mean to 0, and then for S in the stocks, it moves it, giving it the bias and the momentum, and then it shows the history, and then computes the mean of getting me the mean of all the stocks in it. We've seen this sort of thing many times before. I then got some constants. By the way, I want to emphasize that I've named these constants to make it easier to change, starting with 20 stocks, 100 days. And then what I do is I stock sub 1. Stocks 1 will be the empty list. Stocks 2 is the empty list. Why do you think I'm starting with bias as 0? Because what do you think the mean should be if I simulate various things with the bias as 0? If I start at $100 as the average price of a stock, what should the average stock of the stock be? If my code is correct, what should the average price be after, say, 100 days, if there's no bias? Pardon? 100, exactly. Since there's no upward or downward bias, they may fluctuate widely, but if I look at enough stocks, the average should be right around 100. I don't know what the average would be if I chose a different bias. It's a little bit complicated. So I chose the simplest bias, an important lesson, so that there would be some predictability in the results, and I would have some, if you will, smoke test for knowing whether or not I was getting, my code seemed to be working. All right. And initially, well, maybe initially, just to be simple, I'm going to start with momentum equal to false. Because again, it seems simpler to have a model where there's no momentum. I'm looking for the simplest model possible for the first time I run it. And then we looked at this little loop before. For I in range number of stocks, I'm going to create 2 different lists of stocks. One where the moves are the distributions are chosen from a uniform, and the other where they're Gaussian, because I'm sort of curious as to, again, which is the right way to think about this. All right? And then I'm going to just call it. We'll see what we get. So let's do it. Let's hope that all the changes I made have not introduced a syntax error. All right, well, at least it did something. Let's see what it did. So the test on the left, you'll remember, was the one with test 1, I believe, was the uniform distribution, and test 2 was the Gaussian. So, but what should we do first? Well, let's do the smoke test number 1. Is the mean more or less where we expected? Well, it looks like it's dead on 100, which was our initial price in test 2. And in test 1, it's a little bit above 100. But we didn't do that many stocks or that many days. So it's quite plausible that it's correct. But just to be sure, not to be sure, but just to increase my confidence, I'm going to just run it again. Well, here I'm a little bit below 100 in test 2, and test 1 a little bit below 100 as well. You remember last time was a little bit above 100. I feel pretty good about this, and in fact, I ran it a lot of times in my office, and it just bounces around, hovering around 100. Of course, this is the wrong way to do it. I should really just put it in a nice test harness where I run 100, 200, 1,000 trials, but I didn't want to bore you with that here. So we'll see that, okay, we've passed the first smoke test. We seem to be where we expect to be. Well, let's try smoke test 2. What else might we want to see if we got things working properly? Well, I kind of ignored the notion of bias by making it 0. So let's give it a big bias here. Assuming it will let me edit it. All right, we're just going to start it up again. It's the safest thing to do. You wouldn't think it would have. All right, be that way about it. Fortunately, we've been through this before. We know if we relaunch the Finder. Who says the Mac OS is flawless? All right, we were down here, and I was saying, let's try a larger, introduce a bias. Again, we're trying to see if it does what we think it might do. So what do you think it should do with the bias? Where should the mean be now? Still around 100? Or higher, right? Because we've now put in a bias suggesting that it should go up. Well, it wouldn't have hurt it. All right. So let's run it. Sure enough, for 1 we see test 2, it's a little bit over 100. And for test 1, it's way over 100. Well, let's make sure it's not a fluke. Try it again. So sure enough, changing the bias changed the price and even changed it in the right direction. So we can feel pretty comfortable that it's doing something good with that. We could also feel pretty comfortable that that's probably way too high a bias. Right? We would not expect that the mean should be over 160, or in one case 150, after only 100 days of trading. Right? Things don't typically go up 50% in 100 days. They go down 50%, but... All right, so that's good. Oh, let's look at something else now. Let's go back to where a simpler bias here. We'll run it again. And think about what's the difference between the Gaussian and the normal. Can we deduce anything about those? Not, well, let me ask you. What do you think? Yes or no? Anybody see anything interesting here? Yeah.
Well, the variance of the Gaussian seems to be less than the uniform.
The variance of the Gaussian?
Less.
All right, that appears to be the case here, but let's run it again as we've done with all the other tests. So we have a hypothesis. Let's not fall victim to the Oklahoma sharpshooter. We'll test our hypothesis, or at least examine it again. See if it's in some sense repeatable. Well, now what do we see? Doesn't seem to be true this time, right? Not obviously. So we're not sure about this. So this is something that we would need to investigate further. And we would need to have to look at it. And it's going to be very tricky, by the way, as to what the right answer is. But if you think about it, it would not be surprising if the Gaussians at least gave us some surprising, more extreme results than the uniform. Because the uniform, as we've set it up here, is bounded. The minimum and the maximum is bounded. With the Gaussian, there's a tail. And you might every once in a while get this, at least as we've done it in this case, this large move out at the end. You might not. There's nothing profound about this other than the understanding that the details of how you set these things up can matter a lot. Well, the final thing I want to look at is momentum. So let's go back and let's set mo to true here. Well, it doesn't want us to set mo to true here. Ah, there it does. So, and now let's run it and see what happens. What do you think should happen? Anybody? I think you're right. These should curl. We'll see if I can do. Oh, not bad. Let's run it. Well, it's a little hard to see, but things tend to take off. Because once things have started moving, it tends to move in that direction. All right. How do we go about choosing these parameters? How do we go about deciding what to do? Well, we play with it the way I've been playing with it and compare the results to some set of real data. And then we try and get our simulation to match the past and hope that that will help it predict the future. We don't have time to go through to do that a lot. I will be posting code that you can play with. And I suggest you go through exactly this kind of exercise, because this is really the way that people do develop simulations. They don't, out of whole cloth, get it right the first time. They build them, they do what-if games, they play with them, and then they try and adjust them to get them right. The nice thing here is you can decide whether you believe momentum and see what it would mean or not mean, etc. All right, one more lecture. See you guys next week.